In previous Scalativity episodes, I described a very fascinating coincidence, a very fascinating ratio that propels me to continue to look further and further into this Scalativity idea. If you take the mass of our sun, the moons and the planets, and divide those by 127 pounds, you get a number that equals the mass of 127 pounds divided by the mass of a hydrogen atom. You get the exact same number. Now, I call the sun and the stars, that larger massive scale, the cosmic scale. The 127 pounds is about the scale of some human beings. This is the human scale. And the mass of the hydrogen atom, the mass range of the atoms of the periodic chart, is the quantum scale. Now, fractal physics theory argues that the cosmic scale, that very large, and the quantum scale, the very small, are equivalent. They're different in size, they're different in mass, but in other aspects, they're exactly equivalent. There exists also a very large scale, larger than the cosmic scale. I call that the titanic scale. It's equivalent to the human scale. If you existed at the titanic scale, you would see an Earth similar to as you see things on our Earth. There also exists a very small scale called the Lilliputian scale. It's equivalent to the human scale as well. So humans, life, I believe, could exist at the human scale as it does, at the very large scale, the titanic scale, at this very small scale, the Lilliputian scale. In this Scalativity episode, I'm going to present the masses and charges of the stars in our Milky Way Galaxy. Current astronomy, the Big Bang Theory, cannot explain why we have the number of stars in the Milky Way Galaxy or in the universe, nor does it explain how many stars are at each mass, nor does it identify what dark matter is. And current astronomy is totally unaware that massive stars have an enormous positive charge. In fact, every star that has twice the mass of our sun or larger carries an enormous excessive positive charge. The fractal Big Bang Theory calculates all of this, the number of stars in the Milky Way Galaxy and in the universe, the percent of hot, bright stars, typical stars we're used to, at each mass. It also calculates the percent of cold, dark stars at each mass. This is a very significant contributor to the dark matter, the missing mass that you have heard about in current astronomy that has not been identified. Well, we identify it in this simple fractal Big Bang Theory. The percent of stars and their positive charge, that's also identified. Now, there is also another self-similarity between the cosmic scales and the quantum scales that encourages fractal Big Bang Theory is on the right path. I'm looking at nuclear explosion, fission explosions, like the original ones done in the 40s and 50s, not the thermonuclear ones with hydrogen fusing into helium very rapidly and exploding, but fission, which is when large atoms, large nuclei, such as uranium, split into two, releasing neutrons and causing a chain reaction, splitting other uranium or fissile nuclei very rapidly and explodes. Now, this equivalence, the self-similarity between the cosmic scale and the quantum scale is this. There are estimated to be about 1 times 10 to the 23rd stars in our universe that we could see. They're contained within about 100 billion galaxies. So you estimate the number of stars in a galaxy times 100 billion. Now, 1.5 milliseconds into a 500 megaton fission explosion, that would be a very large-scale fission explosion if we would have one on the Earth, and a very short time into it, 1.5 milliseconds, you would have the same number of nuclei of fission products that are undergoing radioactive beta decay. They would be emitting neutrino energy. There would be 1 times 10 to the 23rd, approximately, nuclei in this fission explosion radiating neutrino energy. That number equals the number of stars we see in the Big Bang universe. And so the correlation is actually, I believe, equivalent. The Big Bang universe is a cosmic scale 500 megaton fission explosion, frozen in time so that it appears to be moving extremely slowly. But the Titanic scale, that larger scale, if humans were there or sentient beings are there, they would perceive it happening at a very rapid rate, as quickly as we see, a mushroom cloud, a fission explosion occurring on the Earth. Can nuclear explosions occur naturally? The Earth's uranium is currently over 99% uranium-238 and under 1% uranium-235. These different masses of uranium, similar chemically, are called isotopes. So they're different isotopes of uranium. Both are radioactive, but they decay at different rates. Uranium-235 is the nucleus that fissions when we build fission atomic bombs. When a neutron is captured by a uranium-235 nucleus, it can fission, it could split apart, releasing more neutrons and a lot of energy, and starting a chain reaction that's released very rapidly is the fission explosion. The uranium-238, that's 99%, does not tend to fission. So you need a larger percentage of uranium-235 if you want to make an atomic bomb. In fact, that's the big challenge of nations that are trying to build their own atomic bombs, is finding a way to extract or separate out this smaller amount of uranium-235 out of a sample of uranium and concentrating it to perhaps 3 or 4%. Then you have enough to create a fission bomb. Now, there is conclusive evidence that we had a natural fission reactor operating on the Earth. It operated for thousands of years in an area in Western Africa called, the country is Gabon, about 2 billion years ago. Water moderated the reactor, and there was actually several different sites of a natural, so slow-moving fission. It wasn't an explosion. The heat was generated at a slower pace. If a comet or an asteroid struck the Earth and exploded near these natural uranium fission reactors about 2 billion years ago, the uranium-235 concentration would have been great enough 2 billion years ago that the intense heat and pressure would have triggered a nuclear fission explosion. So you could have had a natural Big Bang universe happen. And if there were sentient organisms, humans, at the Lilliputian scale, riding on one of the neutrons that were decaying, it would appear as a solar system, and the universe, its explosion would appear as our Big Bang appears to us now. 5 countries tested over 2,000 nuclear bombs since 1945. Therefore, the human scale created over 2,000 Lilliputian scale Big Bang universe. Hey, you're welcome, Lilliputians. There are over 400 nuclear fission reactors operating today in electric power plants, sustaining over 400 Lilliputian scale universes. They're non-expanding, they're not exploding, but they would have stars and planets and galaxies appearing to the Lilliputian scale, not too dissimilar, just it wouldn't be expanding, it would be similar to our universe. Before the Titanic scale uranium vein exploded into our universe, it may have operated as a Titanic scale nuclear fission reactor for thousands of years. For all practical purposes, our universe might have existed with stars and galaxies essentially forever before the Big Bang took place. It's very interesting the way nature and these scales are designed. Radioactive material is very hazardous and causes damage to biological organisms that get near it. Consider Chernobyl, that there was a lot of radioactive material released unintentionally, and the area is contaminated, and it could cause mutations and death. The way the fractal universe is organized is that when radioactive material exists, it inhibits biological organisms from going near it. They'll get sick, they'll die, so they leave it alone. But within that radioactive material, there could be this Lilliputian scale universe going on, this tiny universe, and it's somewhat protected because animals, humans, they don't want to go near highly radioactive material. They'll get sick and they'll avoid it. So it's kind of interesting that the only place that life would evolve or would look like our solar system, with humans and animals and plants and life from burning suns and stars providing the energy, would be where radioactive material exists. Now, when a uranium-235 nucleus captures one neutron, it forms a uranium-236 nucleus. 14% of the time, this uranium-236 nucleus emits a gamma-ray photon and remains uranium-236. 86% of the time, the uranium-236 nucleus fissions into 2 large fission products plus a few neutrons. They all have high kinetic energy. The large fission products have too many neutrons, making practically every fission product radioactive. Fission product yield data for uranium-235 struck by fast neutrons has been carefully measured in laboratories. Fission product yields from nuclear fission explosions matches this data. So there's controlled data happening at a slower pace, and you're getting these fission product yield percentages. And that matches what would be released in a rapidly occurring nuclear fission explosion. Astronomers estimate 200 to 400 billion stars shine in our Milky Way Galaxy, and about 100 billion other galaxies exist in the universe. Cosmic scale fission products and cosmic scale uranium have condensed into Titanic scale particles, and they are the billions of spiral galaxies that we see. To release 500 megatons of energy would require 73 times 10 to the 27 uranium nuclei to fission into about twice as many fission products during the microsecond just before the explosion. So solid matter, 500 megatons of uranium enriched in 235, this enormous number of nuclei would fission. It would happen all very quickly. The solid material changes to a gas, and then the explosion event occurs. Now, if you divide that number by 100 billion, you can get the estimate for the number of cosmic scale fission products in our galaxy. Basically, the fission product yield from uranium fission in one particle. That is how fractal physics theory, the fractal Big Bang theory, calculates the number of hot burning in our Milky Way galaxy. Now, only a fraction of the cosmic scale fission products are emitting cosmic scale neutrino energy at any moment, appearing as visible stars. So the visible distribution of cosmic scale fission products differs somewhat from the invisible distribution of cosmic scale fission products. So the actual fission product yield data needs modified a bit. It's out there. It's in particle form compared to the Titanic scale, what we would call as galaxies relative to the human scale. But a lot of that is the dark matter. A lot of those nuclei are not visible in any way. They're the missing mass. Only a percentage of it is undergoing beta decay, radiating antineutrino energy, what we see as stars. Radioactive decay rates combined with fission product yields determines the number of each nucleus radiating neutrino energy 1.5 milliseconds after the explosion. These numbers add up to 192 billion cosmic scale fission products shining as massive stars in our Milky Way galaxy. Of these 192 billion massive stars, 74% have masses ranging from 89 to 103 times the Sun's mass. 12% have masses ranging from 141 to 147 times the Sun's mass. These 192 billion massive stars can be grouped as Titanic scale elements. 68% are Titanic scale solids: rubidium, strontium, yttrium, zirconium, and niobium, while 7% are Titanic scale noble gases: krypton and xenon. Our galaxy also contains, albeit by rough estimate, 2 million trillion cosmic scale neutrons flowing in all directions at various speeds. They're colliding with cold dark stars and hot bright stars elastically. They're colliding with cold dark stars and hot bright stars inelastically. I believe perhaps detected as gamma ray bursts. 3 trillion have already decayed, passed through a phase like our current solar system. They've decayed, they've changed into 3 trillion cosmic scale hydrogen atoms. 1.5 billion are currently decaying and appear similar to our solar system. Many are being absorbed by cosmic scale uranium nuclei. Fission products already have too many neutrons and don't absorb more neutrons. With so many cosmic scale neutrons remaining to decay into solar system, I am awestruck that 1 million habitable planets will always be available in our galaxy for life to exist on, essentially forever. Now, to summarize, the Milky Way galaxy, 7 categories of star estimates currently exist in fractal Big Bang theory. There are 192 billion hot bright stars ranging from 66 to 172 solar masses. 1.4 million trillion cold dark stars ranging from 66 to 172 solar masses, waiting their turn to shine. 1.5 billion sun-like solar systems. 1.8 million trillion cold dark stars, each the mass of our solar system. These are cosmic scale neutrons. 3 trillion cold dark stars, with some still cooling, each the mass of our Sun. These are cosmic scale hydrogen nuclei. 17 million trillion cold dark stars with 238 solar masses. These are cosmic scale uranium nuclei. 35 million trillion cold dark stars with 16 solar masses. These are cosmic scale oxygen nuclei. All these add up to 55 million trillion stars in the Milky Way Galaxy. Subtracting out the cosmic scale neutrons leaves 53 million trillion cosmic scale atoms forming our galaxy. A simple dimensional check is made on this fractal model of our galaxy. The total Milky Way Galaxy volume is calculated from the disk area times the disk thickness. 100,000 light years is used for the disk diameter, and 6,000 light years is used for the disk thickness. The average cosmic scale atomic volume is scaled from an atomic volume of radius 1.5 angstroms. Dividing the galaxy volume by the average cosmic scale atomic volume equals 52 million trillion cosmic scale atoms. These two values are essentially identical. Both values are calculated by fractal physics theory concept, but by vastly different physical methods. 53 million trillion cosmic scale atoms in our galaxy by a cosmic scale nuclear fission explosion. 52 million trillion cosmic scale atoms in our galaxy by a simple ratio of 2 volumes. Is this just a coincidence? It's impossible. We must listen to what the data is telling us. As I said in previous episodes, Horton must hear the who. Fractal physics theory predicts the mass of every star, both seen and unseen, in the entire universe. This scientific paradigm has incredible explanatory power. You should start wondering about all the cosmic scale electrons orbiting cosmic scale cold dark stars and hot bright stars. Fractal physics theory self-similarity demands cosmic scale electrons show themselves. They are there, exactly where expected, but that's for later Scalativity episodes. This Scalativity episode was produced by Z23 Studios. Make sure you subscribe to our Scalativity channel so you don't miss an episode. Please go to scalativity.com to read the 5 initial fractal physics articles published online in the Fundamental Journal of Modern Physics. Scalativity.com also includes 3 groundbreaking, amazing articles available nowhere else. Until the next Scalativity episode, this is Leonard Malinowski, inviting you to help me advance physics.